Alright guys, we're going to start going over the MATLAB portion for our Find Sun Sensor lab. We'll go over this section by section, starting with section number 1, where we define some of the sensor geometry. We're going to start out by just doing some cleanup. This is good practice to do this at the beginning of any MATLAB script that you're making. You're going to clear all your variables, get rid of everything in your command window, and close any figures that you currently have open. So we're going to start by defining the height. The height is the distance from the top of your photoresistors to the top surface where your slits are on the top of your sensor configuration. Number of sensors, that's just how many sensors you have in one single sensor array. So we have 2 arrays, each with 12 sensors for a total of 24 sensors. This is the width in inches of each sensor that you're using. Height is also in inches. It doesn't really matter what unit you're using, just as long as they're consistent. L is the length of your sensor array. That's just the width of each sensor that you define here times the number of sensors. And then we have a few variables here that just help calculate what your field of view is. If we run this section with this specific geometry, we see that we have a field of view of 88.37 degrees. And that's good. We're aiming for 90 degrees. It's pretty close. All right, in this section, we're going to plot the hemisphere in a figure. And the reason we're doing that is it makes it really easy to visualize where the sun is in the reference frame of the sensor configuration. So in order to do that, there's a pretty simple way to do it. We're just gonna basically plot half of a sphere on a plane. So you can do that very easy with the function sphere. It's a built-in MATLAB function, and you can define what the radius you want your sphere to be. This section of code is basically saying we want to scale whatever sphere we're creating so that it has a radius of 1, and we only want to take the top half of it. The reason we want that is because we basically just want one hemisphere for the entire sphere. Next up, we're going to actually plot it, and we're doing that with the command surf. There are a few extra variables you can put in here, like the color you want to make it. You can play around with that if you want. Next up, we're going to make our axes equal. If you don't do this and you just do surf, it's going to look like a sphere that's been pulled in one direction. It just doesn't look that good. So if you do axis equal, that's going to make your X, Y, and Z axes all have the same units, and it'll all look equal. Next up, you'll see later on in the code that we're going to be plotting things on top of each other, but we want to lock down our hemisphere because that's not going to change. So we're going to get the current axis that we just plotted on with our surf command. We're going to hold on to it, and we're also going to turn the axis off. And you'll see why a little bit later in the code. We also want to pause briefly after we plot this. Sometimes MATLAB, if you don't have a pause after you plot something and your code is running very quickly, it's not actually going to plot it until it encounters a small pause in your code. So we just put in a 3-second pause, and we're going to print that to our command window just to make sure that we get that hemisphere plotted correctly. Alright guys, so in this section we're going to develop our serial connection with the sun sensor configuration with the Arduino. This first command is going to delete any existing COM port connections that we have. And the reason you want to do that is because MATLAB will often throw an error if you are watching a serial monitor connection in the Arduino program while you are simultaneously trying to open a COM port in MATLAB. So this just deletes any COM connections that you already have to make room for the one you're about to create. Line 30, you're just designating what COM port you're using. You can look this up in your Arduino program by going to the Tools, Port, and then you can select which port you're using. For us, it's often been 7, and that's going to be stored in the variable called S. These next 4 lines of code are pretty standard. A lot of them are default values. For instance, we're using 9600 as our baud rate. You shouldn't have to mess with these 3 lines. If you need to, there's a ton of documentation online for MATLAB on serial connections and the different parameters that you can mess around with. All right, this line is going to formally open that serial connection. These last two lines are variables that we'll see pop up later in our code, and we're just initializing them now. So we'll go over those specifically in a different section. All right, guys, so we're going to start going over the calculations in this MATLAB script. So to start out, these first two lines are variables that are going to be referenced a little bit later in the code, and I'll make sure to point those out and come back to this spot when they're actually used in the code. All right, so this is one of the bigger loops in the code. It's a while loop. While in operation is equal to 1 or true. The variable in operation is the one that we set up here, which is equal to 1, and that pretty much never changes. So that means this while loop is going to repeating over and over and over and over again until we manually cancel the program. All right, so temp data is a variable that gets set to the line of data that is received from our serial port. So fgetS is a command that gets the latest line of data from the serial port. So once that is stored in temp data, we check to see if its length is equal to 121 characters. Now 121 is the length of the ideal string of data that we're going to get. Sometimes the Arduino may freak out and send some line of data that is either corrupt or it contains more data points than we really want. And we don't want to read in those lines because it's going to screw up our MATLAB program. So we want to make sure that it's correct length. And if it is the correct length, then we're going to take in that variable, temp data, and we're going to parse it, and we're going to split it up into different strings. Now strsplit splits this string, and it splits it in between every comma that it finds. And now that's stored into temp data. It just overrides the old variable. We're going to override it once again, and we're going to generate, actually temp data up here makes a new cell array once it splits the string of the original temp data. So now we want to convert every string that's in temp data into a number, because that's basically what they are. We're getting a whole bunch of numbers. We need to apply the function string to number to every single element in that cell array. You can do that with the function cellFun, and that applies this function to every element in this cell array. Once we've done that, we can split our data into the X and Y axes. In our specific setup, the X axis is the line of 12 photoresistors that is going to give us information on our X axis in the reference frame of the sun sensor configuration. And so that just happens to be that those are sensors 13 through 24. You can see down here our Y axis are sensors number 1 through 12. So we're extracting our X-axis information from our temp data vector, and then we want to find the maximum value within X-axis. The reason we're doing that is because we want to find the one photoresistor that has the highest voltage out of that entire array of photoresistors. So we'll use the function max, and we're going to record what that maximum value is as well as its index in that vector. We also want to find the second largest value in that array. So in order to do that, once we find the maximum value, we're going to set it equal to 0, because that's basically the minimum that we can get. And then we're going to do the exact same function to the exact same vector, but now that the maximum value is 0, this function is going to turn basically the second largest value. And we're going to record that value, and we're going to record its index in that vector. We do the exact same thing down here. It's the exact same thing for the y-axis. We're going to get down to offset x, and we have offset y. I'll explain what that is in a second. For each axis, we have an array of 12 photoresistors, and we can split that into two sections of 6 resistors. Now let's say the incident sun ray is hitting directly in between those two groups of 6 photoresistors. That means that the base of the triangle that we're trying to measure is going to be measured from that spot in between the 6th and 7th photoresistor. We basically want to figure out the index of the photoresistor that has the highest voltage and find how far away it is from that midpoint. in between numbers 6 and 7. And so what offset is it's a variable that says whether you want to measure the distance to the middle of the photoresistor or to the outsides of one of the photoresistors. If we're able to find one photoresistor that has a maximum value, we're going to take the index of that one photoresistor and measure the distance to its center. Now let's say we have two maximum values in the array, and those different indices happen to be right next to each other. That means that the incident sun ray is probably hitting both photoresistors. So the distance that we use in our calculation should be the distance from the center of the array between photoresistors numbers 6 and 7 and the midpoint in between those two resistors that the light is hitting. So basically that is what offset takes care of, is it basically tells us whether we want to go to the center of a resistor or in between two different resistors. So this if statement is saying if the indices of the maximum two photoresistors are only one apart, so that means they're right next to each other. If those two happen to be next to each other, we're going to take the minimum indice out of the two maximum, and we're going to set the offset equal to 0. And the reason is once we actually calculate the distance from the midpoint to that point in between photoresistors, we're using the dimension that we specified at the top of the code of width of each sensor. So we're going to multiply the width times however many photoresistors it takes to get to that indice. All right, so as I said, it's the exact same thing for y-axis and x-axis. Our offset, though, is going to be defined as different variables. We have offset x and we have offset y. Once we have those offsets, it's time for us to start calculating angles. It just so happens that the equations we're going to use to calculate those offsets are going to be different for if our indice is between 1 and 6 or between 7 and 12. So you can see, again, we have lots of similarities between the calculations for y-axis and x-axis. There's going to be a lot of repetition. We have one if statement for if the indice is between 1 and 6. The same thing down here, 1 and 6, between 7 and 12, between 7 and 12. And then we also have a separate one saying if it's smack in the middle, if the two maximum indices are number 6 and number 7, then the zenith angle is going to be 0 because that means the incident light is coming from directly above the sensor. So within each if statement, we're going to be measuring a distance, and that distance is the distance from the origin, which is basically defined as the barrier in between photoresistor number 6 and number 7, and the indice of the maximum voltage on the photoresistor. Once we have that distance, we can use that distance and the height that we defined at the beginning of this MATLAB script to calculate the zenith angle. And that zenith angle is crucial in the calculations in figuring out the elevation and azimuth angles later on in the code. So as you can see, there are a few small similarities, or differences, between calculating the zenith angle if the maximum index is between 1 and 6, or if it's between 7 and 12. Here we have 90 minus the inverse tangent of height over distance, and over here we have negative 90 minus the inverse tangent of height over distance. So as I said before, these calculations are the same for y and x axes, and we will go on to talk about the calculations when we determine the sun vector.